Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a quarter circle, AOB is a quarter circle, and we also have tangent QP, that is tangent to this quarter circle here at this point. We know that PQ equals to 3 units in its length. And side AP equals to 6 units in its length. This is side, this angle BQP is the right angle, and this is angle APQ, that is equals to 90 degrees inside. Again, our mission is to find out the area of this green shape. Okay, so first of all, we define the point of tendency of tangent QP with this quarter circle, this point S. And we join points O and S together by a straight line. So point O is the center of the quarter circle, point S is the point of the quarter circle itself. Therefore OS is the radius of the quarter circle. So I write it down. OS is the radius. And we define the radius of the quarter circle as x. Therefore OS equals to x, it is the radius of the quarter circle. You can implement here rule 1. We have the radius OS, that is 1 to point S, that is the point of tendency of tangent QP with this quarter circle. And whenever you have a radius that is 1 to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say from point B, we will do perpendicular on OS. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS, this point SM. So actually, by doing this construction, we can do here quadrilateral BMSQ. So inside this small quadrilateral BMSQ, we have 1, 2, 3 right angles, and the sum of 3 right angles is 270 degrees, plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its size. So inside quadrilateral BMSQ, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this 4 quadrilateral BMSQ as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle BMSQ, side BQ is equal to the opposite side MS. but BQ equals to 3, therefore MS must be also equal to 3 units in its length. So write it down. Side MS equals to 3 units. We also have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle BMSQ, side BQ is parallel to the opposite side MS. So I write it down. In the small rectangle BMQS, side BQ is parallel to the opposite side MS. Repeat again. In rectangle BMQS, side BQ is parallel to the opposite side MS. So BQ is parallel to MS. OS is the radius of the quarter circle. So OS is a radius, it is absolutely a straight line. And we know that part of the straight line OS, that is MS, is parallel to BQ. Therefore the straight line OS itself must be also parallel to BQ. So write it down. The straight line OS must be also parallel to BQ. Okay. So actually, in quadrilateral OBQS, in this quadrilateral OBQS, side OS is parallel to side BQ. Side OS is parallel to side BQ. Therefore, quadrilateral OSBQ is a trapezoid. Quadrilateral OSBQ is a trapezoid. Why? Because the definition of a trapezoid is a quadrilateral with one pair of parallel sides. So quadrilateral OBSQ is a trapezoid. So what is the length of this line segment? Line segment OM. For the moment it is very easy to see that OM equals to OS minus MS. Again, OS minus MS equals to OM. So I write it down. OM equals to OS minus MS. So OM equals to OS, that is the radius of the quarter circle, that is equal to X according to our definition, minus MS, that is 3. So in conclusion, we found out that OM equals to X minus 3 units in its length. Okay, so I write it down here. Line segment OM is equals to X minus 3 units in its length. In the next step, we do another construction. That is to say, from point A, we do perpendicular on OS. Again, from point A, we do perpendicular on OS. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So actually, by doing this construction, we can do quadrilateral ANSP. Inside this quadrilateral ANSP, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral ANSP, we have 4 angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to the quadrilateral ANSP is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANSP, side AP is equal to the opposite side NS. But AB equals to 6, therefore NS must be also equal to 6 units in its length. So I write it down. NS equals to 6 units. Likewise, we know that the opposite sides of a rectangle are parallel to each other. So in rectangle ANSP, side AP is parallel to the opposite side NS. So I write it down. In rectangle ANSP, side AN is parallel to side SN, side AP is parallel to side SN. Repeat again. In rectangle ANSP, side AP is parallel to the opposite side, side SN. But here, side SN is part of the straight line OS. Again, side SN is part of the straight line OS. So if part of a straight line is parallel to another straight line, then the straight line OS itself must be also parallel to the other straight line, that is AP. So OS must be also parallel to AP. Again, OS is parallel to AP, therefore in quadrilateral OSPA, in this quadrilateral OSPA, side OS is parallel to side AP, therefore quadrilateral OSPA is a trapezoid. Okay, quadrilateral OSPA is a trapezoid. Why? Because it has one pair of parallel sides. That is to say, side OS is parallel to side AP. Here again, for the other OSPA is a trapezoid. Okay, so what is the length of this line segment ON? From the drawing, it is very easy to see that ON equals to OS minus NS. Again, OS minus NS equals to ON. So I write it down. ON equals to OS minus NS. So ON equals to OS. OS is the radius of the quarter circle that is equal to X, according to our definition, minus NS. NS equals to 6. So in total, ON equals to X minus 6 units in its length. ON equals to X minus 6 units in its length. In the next step, we focus on the right angle triangle ONA. In the right angle ONA, we define this angle as alpha. So in the right triangle ONA, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equals to 180 degrees. So the missing angle here equals to 90 degrees minus alpha. We define 90 degrees minus alpha is beta. Therefore, the missing angle here must be equal to beta. If 90 degrees minus alpha equals to beta, it means that 90 degrees minus beta equals to alpha. So just subtract beta and then add alpha to this equation, we'll get that 90 degrees minus beta equals to alpha. Very simple. Okay. So, what is the size of this missing angle? Actually, the size of this missing angle will be equal to the size of the big angle, that is equals to 90 degrees, minus the size of this angle, that is equal to alpha. So 90 degrees minus alpha equals to the missing angle. Again, angle A or B, that is 90 degrees, minus this angle alpha equals to the missing angle. That is to say, the missing angle equals, this missing angle equals to 90 degrees minus alpha, but we already found out, according to our definition, 90 degrees minus alpha equals to beta. Therefore, the missing angle equals to beta. So inside the right triangle OMB, this angle equals to beta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus beta. But 90 degrees minus beta equals to alpha. 90 degrees minus beta equals to alpha, so the missing angle equals to alpha. So, what is the definition of line segment OB? Line segment OB starts from the center of the quarter circle, that is to say from point O, and ends at point B, that is a point on the quarter circle itself. This is exactly the definition of a radius. So OB is equal to the radius of the quarter circle, is equal to x. OB equals to x units in its length. Likewise, what is the definition of line segment OA? Line segment OA starts from the center of the quarter circle, that is to say from point O, and that's at point A, it is the point on the quarter circle itself. Therefore, OA is also the radius of the quarter circle, that is equal to x, according to our definition. So, in the next step, we will prove that those two right triangles can go into each other. That is to say, we will prove that the right triangle ONA is congruent to this right triangle, triangle OMB. So I write it down. We will prove that the right triangle ONA congruent to this right triangle, triangle OMB. So why those two right triangles can go into each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this is angle ONA in the right triangle ONA, and it is equal to this angle, that is actually angle OMB in the right triangle OMB. And fill again, angle ONA in the right triangle ONA equals to angle OMB in the right triangle OMB. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. So actually, this is angle AON in the right triangle ONA, and it is equals to this angle. This is actually angle OBM in the right triangle OMB. So until again, angle AON in the right triangle ONA equals to angle OBM in the right triangle OMB. They are both equal to alpha, therefore they are equal to each other. And those two angles, they are both equal to beta, therefore they are equal to each other. So actually this is angle OAN in the right triangle ONA, and it is equals to this angle. That is actually angle BOM in the right triangle OMB. So I repeat again, angle OAN in the right triangle ONA equals to angle POM in the right triangle ONB. They are both equal to beta, therefore they are equal to each other. So we actually proved that all the triangles in this right triangle ONA are correspondingly equal to all those to all the triangles in this right triangle OMB. And finally, side OA in the right triangle ONA is equals to this side, that is side OB in the right triangle OMB. They are both the radii of the circle that is equal to x, therefore they are equal to each other. Repeat again. Side OA in the right triangle ONA equals to side OB in the right triangle OMB. They are both the radii of the circle that is equal to x, therefore they are equal to each other. So we actually proved that the right triangle ONA congruent, this is the sign of congruent, to the right triangle OMB according to angle side angle rule. Okay, so what is angle side angle rule? Angle side angle rule is that if we prove that two angles and the side that is included between the two angles in one triangle are correspondingly equal to two angles and the side that is included between the two angles in a second triangle, then we actually proved that the two triangles can point to each other according to angle side angle rule. And here we proved that those two angles alpha and beta and the side that is included between those two angles, that is actually side OA in the right triangle ONA, are correspondingly equal to those two angles that are also alpha and beta, and the side that is included between those two angles, that is side OB in the right triangle OBM. Therefore, those two right triangles can go to each other according to angle side angle rule. And from the fact that those two right triangles can go to each other, we will derive that side ON in the right triangle ONA equals to side MB in the right triangle OBM. So I'll write it down. We derive that side ON in the right triangle ONA equals to side MB in the right triangle OBM. Then again, we derive the side ON equals to side MB. But we have already found out that ON equals to x minus 6. ON equals to x minus 6. So we can write here that ON equals to x minus 6. And from this equation, x minus 6 equals to ON equals to MB. We will derive that MB also equals to x minus 6. So here and b equals to x minus 6 units in its length. Likewise, from the fact that those two right angles can go into each other, we will conclude that side OM in the right angle OBM is equal to side AN in the right angle ONA. So I write it down. Side OM in the right angle OBM equals to side AN in the right angle OAN. Side OM equals to side AN according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say OM and AN, must be also equal to each other. But we have already found out that ON equals to x minus 3. So we can write here that OM equals to x minus 3. And for this equation, x minus 3 equals to OM equals to AN, we will derive that AN is also equals to x minus 3 units in its length. So this is side AN, that is equals to x minus 3 units in its length. In the next step, I will copy the right triangle AON in a new page, and we will implement on this right triangle AON the Pythagoras theorem. Here by PT is the version from Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. AN equals to x minus 3, ON equals to x minus 6, and the hypotenuse OA equals to x. It is also the radius of the quarter circle that is equal to x according to our definition. So actually, this is the right triangle AON that I copied from the original drawing. So according to the Pythagoras theorem, AO squared equals to ON squared plus NA squared. AO equals to x, therefore AO squared equals to x squared. And it is equals to ON squared. ON equals to x minus 6, therefore ON squared equals to x minus 6 squared plus NA squared. NA equals to x minus 3, therefore NA squared equals to x minus 3 squared. So in conclusion, we found out that x squared equals to x minus 6 squared plus x minus 3 squared. So x squared equals to x minus 6 square. X minus 6 square equals to x square plus 6 squared, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 square. X minus 3 square equals to x square plus 3 squared, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. So this side of the equation we left with nothing, this is to say 0. This is equals to, in the other side of the equation we have 36 plus 9, that is 45. And we also have minus 12x minus 6x, that is minus 18x. plus x squared. Actually, in conclusion, we found out that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared minus 18x plus 45 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. So in the next step, we put the data inside the general formula for our specific quadratic equation, and we find out the value of the values of x. X is the radius of the quarter circle. So according to the general formula, in our specific quadratic equation, x will be equal to minus b. B is minus 18, so minus b is minus 18, that is plus 18, plus minus square root of b squared. B is minus 18, so b squared is minus 18 squared, that is 324, minus 4 times a is 1, so minus 4 times 1 is minus 4, times c, that is 45, so minus 4 times 45 is minus 180 over 2a. A is 1, so 2 times a is 2 times 1, that is 2. So we found out that x equals to 18 plus minus square root of 324 minus 180 is 144, so inside the root we left only 144 divided by 2. So x equals to 18 plus minus the square root of 124 is 12 over 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12 over 2. 18 plus 12 is 30, and 30 over 2 is 15. So according to the first solution for x equals to 15 units in its length. And according to the second solution, we have also another solution, that is the second solution. According to the second solution, x equals to 18 minus 12 over 2. 18 minus 12 is 6, and 6 over 2 is 3. So I found out that according to the second solution, x equals to 3 units in its length. But this solution is an incorrect solution. Why? Because we have already found out that the length of this line segment BM equals to 6. So BM equals to 6 units in its length. So BM is a length, and as a length it must be a positive number. That is to say, BM is equal to 6 units, it must be a positive number. So Bm is equal to 6, it must be a positive number. It means that it must be greater than 0. Again, x is a length, and as a length it must be a positive number, or x must be a positive number. So we have here x minus 6, bm, again bm equals to x minus 6, bm equals to x minus 6 units in its length. Okay, so bm is a length, and as a length it must be a positive number. So bm that is equal to x minus 6, it must be a positive number. So x minus 6 must be greater than 0. If x minus 6 must be greater than 0, it means that x must be greater than 6. So x must be greater than 6. So if x must be greater than 6, x can never be equal to 3, that is less than 6. So this solution is incorrect solution, so we cancel this solution, and we have to live with the first solution that is possible for x, that is actually x equals to 15 units in its length. So x equals to 15. So in the next step, I will present to you the general formula for the area of a trapezoid. I repeat again, a trapezoid is a quadrilateral with one pair of parallel sides. So we have here quadrilateral ABCD. This quadrilateral ABCD, side AD is parallel to the opposite side BC, therefore quadrilateral ABCD is a trapezoid. So what is the area of trapezoid ABCD? Before that, the two parallel sides, that is to say side AD and side BC, are defined as the bases of the trapezoid. So AD is the first base and BC is the second base. So the area of trapezoid ABCD equals to the sum of its bases, that is to say it is AD plus BC times the height to the base over 2. The height must create 90 degrees with the two bases. So if CD creates 90 degrees, that is to say, if this angle equals to 90 degrees and this angle also equals to 90 degrees, then the height is CD. But if CD doesn't create 90 degrees with the two bases, then we'll just draw perpendicular to one of the bases, and the perpendicular will be the height. In conclusion, found out that the area of trapezoid ABCD could be any trapezoid, so the area of a trapezoid equals to the sum of its bases, that is actually AD plus BC times the height to the base over 2. The height to the base must create 90 degrees with the base. Okay, so what is the area of this ring shape the area of the green shape is equals to the area of this whole shape in total minus the area of this quarter circle A or B. Again, the area of the whole shape in total minus the area of quarter circle A or B equals to the area of the green shape. But because of the fact that the area of the whole shape, this is to say whole shape OAPSQB, consists of those two trapezoids. So the sum of the areas of those two trapezoids will be equal to the area of the whole shape. So the area of those two trapezoids, that is the area of the whole shape minus the area of this quarter circle A or B, equals to the area of the green shape. Okay, so if we're going further, actually the area of the green shape equals to the sum of the areas of those two trapezoids. That is actually the area of the whole shape. So this is the area of trapezoid OBQS plus the area of the second trapezoid, it's actually trapezoid OSPA again the sum of the areas of the two trapezoids, that is to say OBQS plus the area of trapezoid OSPA, is equals to the area of the whole shape in total, and the area of the whole shape in total minus the area of quarter circle A or B will be equal to the area of this green shape. So it is minus the area of this quarter circle A or B. Repeat again, the area of the green shape equals to the area of the whole shape minus the area of the quarter circle A or B. But the area of the whole shape equals to the area of trapezoid OBQS plus the area of trapezoid OSPA, because the area of this whole shape or trapezoid or this whole shape OAPSQB consists of those two trapezoids. Therefore, the area of those two trapezoids will be equal to the total area of shape OAPSQB. So the area of the whole shape, that is the sum of the areas of those two trapezoids minus the area of this quarter circle A or B, equals to the area of the green shape. So what is the area of trapezoid OBQS? The area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height. The height is QS. Why the height is QS? Because of the fact that the height and QS creates 90 degrees with two bases. This angle equals to 90 degrees and this angle also equals to 90 degrees. So the height is QS over 2. So the sum of the bases times the height over 2 is the area of trapezoid OBQS plus the area of trapezoid OSPA. The area of trapezoid OSPA equals to the sum of its bases, that is actually OS plus PA, times the height, the height is SP. Why? Because of the fact that the SP creates 90 degrees with the two bases. Those two angles are both right angles. So the height is SP divided by 2. In conclusion, we found out that the area of trapezoid OSPA equals to the sum of its bases, that is OS plus PA, times the height, that is SP over 2, minus the area of the quarter circle, or A or B. What is the area of quarter circle A or B? The area of the quarter circle A or B equals to the area of the circle over 4. But quarter circle is a quarter of a circle. Therefore, the area of the circle over 4 equals to the area of the quarter circle. The radius of the quarter circle is the sum of the radius of the circle. So, and the radius is x. Therefore, the area of the circle equals to pi x squared. And then when we divide the area of the circle by 4, we get the area of the quarter circle A or B. So, what is the area of trapezoid OBQS? This equals to BQ, that is 3, plus OS, that is 15, it is the radius of the quarter circle, that is 15, times the height QS equals to x minus 6, x is 15, so 15 minus 6 is 9 over 2. In conclusion, we found out actually that the area of trapezoid OBQS equals to 3 plus 15, that is 18, 18 over 2 is 9, and 9 times 9 is 81. So in conclusion, we found out that the area of trapezoid OBQS equals to 81 square units, plus the area of trapezoid OSPA. The area of trapezoid OSPA equals to OS, that is 15, plus PA or AP, that is 6, times SP. SP equals to x minus 3, x is 15, so 15 minus 3 is 12. So the height is 12 over 2. So 15 plus 6 is 21, and 21 times 12 over 2, that is 6, so 21 times 6 is 126. So in conclusion, we found out that the area of trapezoid OSPA is equal to 126 square units minus the area of the quarter circle A or B. The area of the quarter circle A or B equals to pi x squared over 4. So it is pi, x is 15, therefore x squared is 15 squared, that is 225 over 4. So in conclusion, we found out that the area of the quarter circle A or B equals to 225 pi over 4, that is actually 176.716 square units. And the area of the green shape equals to the sum of the areas of those two trapezoids. This is actually 81 plus 126, that is 207. This is to say, the sum of the areas of those two trapezoids is equals to 207 square units, minus the area of the quarter circle A or B, that is 176.716 square units. So 207 minus 126.716 equals to 30.285 square units. So in conclusion, found out that the area of the green shape is equals to 30.285 square units. That is the answer to the question. Repeat again. The area of this green shape is equals to 30.285 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So in the domain, we have a quarter circle. AOB is a quarter circle. And we also have here tangent QP that is tangent to this quarter circle here at this point. BQ equals to 3, AP equals to 6. This is angle BQP that is a right angle, and this angle APQ is also a right angle. Again, our mission is to find out the area of this green shape. So, in the first step, we define the point of tendency of tangent QP if this quarter circle this point is point S. Then we join points O and S together by straight line. Point O is the center of the quarter circle, point S is the point of the circle itself, therefore OS is the radius of the quarter circle. And according to our definition, the radius of the quarter circle equals to X, therefore OS equals to X. Then we implemented the rule 1. We have the radius of OS that is 1 to point S, that is the point of tendency of tangent QP with this quarter circle. Whenever you have a radius that is 1 to the point of tendency, then tangent QP will be perpendicular to the radius FSO. So if QP is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say from point B, we do perpendicular on OS. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS as M. So inside quadrangle BMSQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees in its size. Therefore, inside quadrangle BMQS, we have 4 right angles. Any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we will relate to this quadrangle BMSQ as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BMSQ, side BQ must be equal to side MS. But BQ equals to 3, therefore MS must be also equal to 3. And we also have the rule that the opposite sides of a rectangle are parallel to each other. So in rectangle BMSQ, side BQ must be parallel to the opposite side MS. Okay, again, in rectangle BMSQ, side BQ must be parallel to the opposite side MS. So we know that BQ is parallel to MS. OS is the radius of the quarter circle, therefore it is absolutely a straight line. So OS is a straight line, and part of the straight line OS, that is MS, is parallel to BQ. So if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, the straight line OS must be also parallel to BQ. Okay, again, the straight line OS must be also parallel to BQ. Then we found out the length of this line segment OM. OM equals to OS minus MS. Again, OM equals to OS minus MS. OM equals to OS minus MS. So OM equals to OS, that is X, minus MS, that is 3. So in total, OM equals to X minus 3. Here, OM equals to X minus 3. Then we did another construction, that is to say from point A, we do perpendicular on OS. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So by doing this construction, we created quadrangle ANSP. Inside this quadrangle ANSP, we have 1, 2, 3 angles. Therefore, this fourth missing angle must be also equal to 90 degrees. So inside quadrangle ANSP, we have 4 right angles. Any quadrangle that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrangle ANSP as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ANSP, side AP must be equal to the opposite side NS. But AP equals to 6, therefore NS must be also equal to 6 units in its length. NS equals to 6 units in its length. Likewise, we also know that the opposite sides of rectangle are parallel to each other. So in rectangle ANPS, side AP is parallel to the opposite side NS. Repeat again, in rectangle ANSP, side AP is parallel to the opposite side NS. So we know that AP is parallel to NS. But NS is part of the straight line OS. So part of the straight line OS is parallel to AP, therefore the straight line OS itself must be also parallel to AP. Okay? The straight line OS must be also parallel to AP. So OS is parallel to AP, so in quadrilateral OSPA, side OS is parallel to side AP, therefore quadrilateral OSPA is a trapezoid. So quadrilateral OSPA is a trapezoid because it has one pair of parallel sides. And the definition of a trapezoid is a quadrilateral that has one pair of parallel sides. Okay. Then we found out the length of this line segment ON. ON equals to OS minus NS. Again, ON equals to OS minus NS. Yeah, ON equals to OS minus NS. So ON equals to OS, that is X, minus NS, that is 6. Yeah, NS is 6. So in total, ON equals to X minus 6. ON equals to X minus 6. Then we focus on this right triangle, triangle ONA. In the right triangle ONA, we define this angle as alpha. So in the right triangle ONA, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So the missing angle equals to 90 degrees minus alpha. We define 90 degrees minus alpha as beta. Therefore, the missing angle equals to beta. Then we found out the size of this missing angle. The size of this missing angle must be equal to the size of the big angle, that is the right angle, is equal to 90 degrees. Angle AOB equals to 90 degrees minus this angle alpha. Again, the big angle that is 90 degrees minus alpha equals to the missing angle here. Therefore, this missing angle equals to 90 degrees minus alpha, because the big angle equals to 90 degrees. So the missing angle equals to 90 degrees minus alpha. But according to our definition, 90 degrees minus alpha equals to beta, therefore this missing angle equals to beta. So in the right triangle OMB, this angle equals to beta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus beta. But 90 degrees minus beta is alpha, therefore the missing angle equals to alpha. Then, what is the length of OB? OB starts from point O, it is the center of the quadrilateral, and ends at point B, that is the point of the quadrilateral itself. Therefore, OB is the radius of the quadrilateral, that is equal to X according to our definition. OA, exactly for the same reason, OA is also the radius of the quadrilateral, that is equal to X. The next step, we proved that those two right triangles can go into each other. This is to say that the right triangle ONA is congruent to this right triangle, triangle ONB. So why those two right triangles can go into each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to beta, therefore they are equal to each other. So we found out that all the three angles of the right triangle ONA are corresponding equal to all the three angles of the right triangle ONB. And finally, we found side OA of the right triangle ONA is equal to side OB of the right triangle ONB. They are both the area of the circle that is equal to X, therefore they are equal to each other. So we actually proved that this right triangle ONA is congruent to this right triangle ONB according to angle side angle rule. So what is angle side angle rule? Angle side angle rule is that if you put the two angles in the side between the two angles in one triangle are correspondingly equal to two angles and the side that is included between the two angles in the second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. And we actually proved that those two angles, that is to say alpha and beta, in the side included between those two angles alpha and beta, that is actually side OA, in the right angle ONA, are correspondingly equal to those two angles that are alpha, that are also they are also alpha and beta, and the side that is included between those two angles, that is side OB, in the right angle OMB. Therefore, we actually proved that those two right angles can go into each other according to angle side angle rule. And from the fact that those two right angles can go into each other, we will derive that side ON in the right angle ONA is equal to side AB in the right angle OMB. Okay, again, we will derive that side ON is equal to side MB according to the rule that corresponding sides in congruent angles are equal to each other. Those two right angles can go into each other, therefore the two corresponding sides, that is to say ON and BM, must be also equal to each other. Okay, so ON equals to BM, but we have already found out that ON equals to x minus 6. So we can write here that ON equals to x minus 6, and from this equation x minus 6 equals to ON equals to MB, we will derive that MB also equals to x minus 6 units in its length. This side MB equals to x minus 6 units in its length. Likewise, because of the fact that those two right angles can go to each other, we derive from it that side OM is equal to side AN. And side OM equals to side AN according to the same rule that corresponding sides in congruent triangles are equal to each other. But we have already found out that OM equals to x minus 3, OM equals to x minus 3. So we can write here that OM equals to x minus 3, and from this equation x minus 3 equals to OM equals to AN, we will derive that AN also equals to x minus 3 units in its length. Here this side AN is equals to x minus 3 units in its length. In the next step, I copied the right angle AON in a new page and we implemented in this right angle AON the Pythagoras theorem. So this is actually the right angle AON that I copied from the original drawing. Side ON equals to x minus 6, side AN equals to x minus 3, and the hypotenuse AO equals to x. It is actually the radius of the quadricycle that is equal to x. In the right angle AON, AO square equals to ON square plus NA square according to the Pythagoras theorem. AO is x, therefore AO square is x square, and it is equal to ON square. ON is x minus 6, therefore ON square is x minus 6 square plus AN square. AN is x minus 3, therefore AN square is x minus 3 square. So in conclusion, we found out that x square equals to x minus 6 square plus x minus 3 square. So we opened the brackets on this side of the equation and found out that x square equals to x minus 6 square, x minus 6 square. X minus 6 square equals to x square plus 6 square, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 square. X minus 3 square equals to x square plus 3 square, that is 9, minus 2 times x times 3, that is minus 6x. So here we have x square on both sides of the equation, so x square we get cancelled. Here we left with nothing in this side of the equation, so it is 0. In the other side of the equation we have 36 plus 9, that is 45, and we also have minus 12x minus 6x, that is minus 18x, plus x square. And when we found out that x square equals to 18x plus 40, when we found out that this is x square minus 18x plus 45 equals to 0, so this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we found out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, this quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Okay, so here we just put this data inside this general formula in order to find out the value of the values of x in our specific quadratic equation. So according to this equation, x equals to minus b. b is minus 18, therefore minus b is minus 18, that is plus 18, plus minus square root of b squared. b is minus 18, therefore b squared is minus 18 squared, that is 324. Minus 4 times a is 1, so minus 4 times 1 is minus 4 times c, that is 45. So minus 4 times 45 is minus 180 divided by 2a. a is 1, so 2 times 1 is 2. 2a is 2 times 1, that is 2. So x equals to 18 plus minus 324 minus 180 is 144 divided by 2. And the square root of 124 is 12. In conclusion, we found out that x equals to 18 plus minus 12 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12, that is 30, and 30 over 2 is 15. So according to the first solution, x equals to 15 units in itself. We have also a second solution that is possible for x. The second solution for x is that x equals to 18 minus 12, that is 6, and 6 over 2 is 3. So according to the second solution, x equals to 4 units in itself. But this solution is an incorrect solution. Why? Because of the fact that we have already found out that the length of this line 7 pm is x minus 6. Here, bm equals to x minus 6 in its length. So bm is a length, and as a length, it must be a positive number. So the length bm, that is x minus 6, it must be a positive number. That is to say, x minus 6 must be greater than 0. If x minus 6 is greater than 0, it means that x must be greater than 6. But if x must be greater than 6, it can never be equal to 3, that is less than 6. So we cancel this solution, x can never be equal to 3. And we have to only with the first solution that is possible for x, that is to say x equals to 15. So if x equals to 15, OB, that is x, is 15, OA, that is x, is also 15. Here, QS, that is x minus 6, that is 15 minus 6, that is 9, and SP, that is x minus 3, that is 15 minus 3, that is 12. In the next step, I presented to you the formula for the area of any trapezoid. Quadrilateral ABCD is a trapezoid. Why quadrilateral ABCD is a trapezoid? Because of the fact that side AD is parallel to the opposite side BC. And the definition of trapezoid is a quadrilateral with one pair of parallel sides. Therefore, quadrilateral ABCD is a trapezoid. Okay? Because side AD is parallel to the opposite side BC. So what is there? And we know that the two parallel sides, that is to say AD and BC, are defined as the bases of the trapezoid. So AD is the first base and BC is the second base. So the area of this trapezoid ABCD equals to the sum of its bases, that is AD plus BC, times the height to the base. The height to the base must create 90 degrees with the two other bases. So if CD creates 90 degrees with the two other bases, that is to say those two angles are right angles, then CD will be the height. If not, if CD doesn't create 90 degrees with the two other bases, then we will just draw perpendicular to one of the two bases, and the perpendicular will be the height to the base. In conclusion, found out that the area of trapezoid ABC, that could be any trapezoid, equals to the sum of its bases, that is actually AD plus BC, times the height to the base over 2. The height to the base must create 90 degrees with the two other bases. Okay. So what is the area of this green shape? The area of the green shape equals to the area of this whole shape in total. It's actually shape AOBQSP minus the area of this quarter circle AOB. But because of the fact that the whole shape AOBQSPA consists of those two trapezoids, therefore the sum of the areas of those two trapezoids will be equal to the area of the whole shape in total. Okay, so the area of the green shape equals to the sum of the areas of the two trapezoids, trapezoid OBQS plus the area of trapezoid OSPA. Again, the sum of the areas of those two trapezoids will give us the area of the whole shape AOBQPA. Why? Because of the fact that the whole shape consists of those two trapezoids. So the area of the green shape equals to the area of trapezoid OBQS plus the area of trapezoid OSPA minus the area of this quarter circle OBA. So what is the area of trapezoid OBQS? The area of this trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height to the base, that is QS, over 2. QS is the height because of the fact that QS gets 90 degrees with the two bases. So the sum of the bases, that is BQ plus OS, times the height, that is OS, over 2, it is the area of trapezoid OBQS. BQ is 3, OS is 15, QS is 9, divided by 2. 3 plus 15 is 18, 18 over 2 is 9, and 9 times 9 is 81. In conclusion, we found out that the area of this trapezoid OBQS equals to 81 square units, plus the area of this trapezoid OBQOSPA. What is the area of trapezoid OSPA? It is equals to the sum of its bases, that is OS plus AP, times the height SP. Why the height is SP? Because of the fact that the height gets 90 degrees with the two bases. So it is the height SP over 2. OS is 15, PA is 6, SP is 12 over 2. 15 plus 6 is 21, and 21 times 12 over 2 to the 6 is 126. And we found out that the area of trapezoid OSPA equals to 126 square units, minus the area of this quarter circle AOB. The area of the quarter circle AOB equals to the area of the circle over 4. The area of the circle is pi x squared because the radius is x. And when we divide the area of the circle by 4, we get the area of this quarter circle AOB. So the area of the quarter circle AOB equals to pi x squared over 4. X is 15, therefore x squared is 15 squared, it is 225. So in total, the area of the quarter circle AOB equals to 225 pi over 4. 225 pi over 4 is 176.716 square units. So the sum of the areas of those two trapezoids will give us the area of the whole shape in total, and the sum of the areas of the two trapezoids is 81 plus 126, that is 207. So the area of the two trapezoids is 207 square units. That is actually the area of the whole shape in total, minus the area of the quarter circle AOB. The area of the quarter circle AOB equals to 176.716. So the area of the whole shape in total, that is 270 degrees, minus the area of the quarter circle AOB, that is 176.716 square units. It is equals to 30.285 square units. In conclusion, we found out that the area of this green shape equals to 30.285 square units. Okay, thank you very much.